Welcome to all students in our ROSE project conducted by Rayat Shikshan Samstha Satara. I am Shinde SR from Sadguru Gadge Maharaj College, Karad. Today we are going to study the new topic coordination compounds. Weightage for this topic is 5 marks without option and 7 marks with options. In this lecture, we studied about the following points: introduction, types of ligands, terms used in coordination chemistry, effective atomic number, and double salt and coordination complex. First is the introduction. We know what are the coordination chemistry. The branch of chemistry which deals with the study of coordination compounds or complex compounds is known as coordination chemistry. The coordination compounds containing coordinate bond, the coordinate bond which is formed by donating electron pairs towards the electron deficient species, and this bond is denoted by arrow. Now see what is the coordination compounds. Mainly the coordination compounds containing two parts, the central metal ion and second part is the ligands. The central metal ion which is surrounded by the number of oppositely charged ions or neutral molecules. For example, chemotherapy drugs cisplatin, the PT NH3 twice Cl2. This is the cisplatin example. In this example, the platinum is the central metal ion and these are Cl2 Cl groups and NH3 groups. These are the oppositely charged molecules or ions which is surrounded by these central metal ion called as the ligands. We know that there is the mainly two parts, the central metal ion and ligands. In this example, platinum is the central metal ion and the two ammonia molecules and two chloride ions which are the ligands. The coordination compounds acts as the Lewis acid-base interaction. See for example, platinum NH3 twice Cl2. This is the coordination compound. The coordination compounds containing the central metal atom and surrounding atoms. In this example, the platinum is the central metal atom and this ammonia group and chloride group is the surrounding atoms. The central metal atom is the electron deficient and these surrounding atoms which are called as the ligands which are the electron rich centers. The central metal ion, that means they are the electron deficient. The electron deficient atom accept the electron pair and these ligands which are the electron rich center which donate the electron pair. From the concept of the Lewis acid which can accept the electron pair are called as the Lewis acids, and the species which can donate the electron pair are called as the Lewis base. And according to this Lewis theory, in coordination compound, the coordination compound acts as there is the interaction of Lewis acid base because central metal atom is the electron deficient which can accept the electron pair from ligands, and that's why the central metal atom acts as a Lewis acid. And the ligands which are electron rich, they are donated the electron pair towards the central metal atom, and that's why these ligands acts as the Lewis base. That means in the coordination compound this acts as a Lewis acid base interaction. Now see the first, what are the ligands? The ligands are the molecules or ions which are coordinated to the central metal atom or ion in a coordination complex are called as ligands. It is also called as the donor groups. We know that the coordination compound contains the central metal ion and surrounding atoms, and these surrounding atoms which are coordinated with the central metal atom by donating their electron pair, and this type of the ions molecules are called as the ligands, and these ligands are the donor group. In the coordination compound, it is the that means the acceptor, and L denoted, ligands are denoted by L, and central metal atom is denoted by the M. The coordinate bond is denoted by this arrow, and then point of this arrow or head of this arrow towards the acceptor. That means this metal ion accept the electron pair from this ligand, that is the donor group. That's why the point of arrow, this point is towards the acceptor. That means from towards the metal ion. In this, for example, K4FeCN6, this Fe is the central metal ion, and these are the ligands. They are surrounded towards the central metal atom. Also in this example, the cobalt is the central metal atom, and central metal ion, and these are the surrounding atoms or molecules which are called as the ligands. Now see the types of ligands. The ligands, it may be negative ions or positive ions or neutral molecules. The ligands are negative ions or positive ions or neutral molecules. See some examples of these negative ions. These are cyanides, hydroxides, oxides, and nitrides. And positive ions, these nitrosolium ions. Neutral molecules, the ligands which are the carbon monoxide, ammonia, water, and hydroxyl amines. These are the different types, that's negative ions, positive ions, or neutral molecules. Now see the classification of ligands. They are classified according to the presence of their donor atoms. It is classified as monodentate ligands, polydentate ligands, and ambidentate ligands. Mainly they are classified as in this way. The monodentate ligands. Mono means one. That means it has only one donor atom. It has only one point of attachment and coordinate with central metal ion at one site. They are coordinated with the central metal atom from one side. For example, this NH3 group. Ammonia group. The nitrogen atom is the donor atom having the electron pair which is donated towards the central metal ion. That means in this type of ligands there is the only one donor atom and the point of attachment is only one. This type of ligands are called as the monodentate ligands. Then in polydentate ligands, it has two or more donor atoms. It has two or more point of attachment and it coordinates with central metal ion at two or more sites. For example, ethylene diamine. In this example, ethylene diamine, there are the two donor atoms, the nitrogen atoms which having the electron pair. This ligand having the two donor atoms. It has 2 point of attachment. That means it is coordinated from this nitrogen atom, also from this nitrogen atom. That means in this compound, in this ligand, it is coordinated with central metal ion from these two nitrogen atoms. Therefore, it is called as the bidentate ligands. Then ambidentate ligands. The ambidentate ligands available sites are two or more. but it is coordinate with central metal ion at only one site. In the ambidentate ligands, there are the two or more donor atoms, but they are coordinated from only one site. In this, for example, NO2 minus. In this example, there are the two donor atoms, that means nitrogen and oxygen. Both are the donor atoms having the electron lone pair. But in coordination compound, they are coordinated with central metal ion from nitrogen or from oxygen. Only one site. In this type of ligands are called as the ambidentate ligands. Now see the next example, ethylene diamine tetraacetate ion, EDTA ion. The EDTA ion having the 6 attachment towards the central metal ion. It containing the 4 oxygen atoms and 2 nitrogen atoms. Containing the 4 oxygen atoms and 2 nitrogen atoms, both are the donating atom. They donate the electron pairs towards the central metal ion, and therefore this compound is called as the hexadentate ligand, because this compound having the 6 attachment of two attachment sites towards the central metal atom. Hence, it is called as the hexadentate ligands, or these types of ligands are also called as the chelating ligands. When these type of ligands are coordinated with the central metal ion, then this type of compounds are called as the chelating compounds. Now, see this. There are the different types of ligands and different abbreviations which are used in our IUPAC system. Monodentate ligands, that means it having the one donor atom. For example, water called as the aqua, ammonia, amine. Then bidentate ligands, for examples are ethylene diamine, abbreviated as EN, oxalate ion, OX, dimethyl glyoxymato, DMG. Then tridentate ligands, diethylene triamine, di-EN. Then tetradentate ligands, triethylene tetramine, triene. Then hexadentate ligands, ethylene diamine, tetraacetate, EDTA. These are the different examples of the types of ligands. These are monodentate, bidentate, tridentate, tetradentate and hexadentate ligands. Now see the terms used in the coordination chemistry. The first, coordination sphere. The coordination compound containing the central metal ion and ligands. For example, K4FeCN6, when it is dissociated as the K plus FeCN6 4 minus. In this coordination compound, the Fe is the central metal ion and CN, cyanides, are the ligands. What is the coordination sphere? The central metal ion and ligands are enclosed in this square bracket are called as the coordination sphere. Coordination sphere is the central metal ion and ligands which are enclosed in this square bracket are called as the coordination sphere. When the coordination compound is dissociated, then it forms the positive ions and this complex ion. And this complex ion is called as the coordination sphere. And this positive ion is called as the counter ion. That means it dissociates as counter ion and coordination sphere. Now, the term used in this coordination compound is the charge number of complex ion. Then what is the charge number? The net charge carried by complex ion is called its charge number. We know that the coordination compound dissociate as counter ion and complex ion, and the complex ion carried its charge, and this charge is called as the net charge of this complex ion is called as the charge number. It is also equal to the algebraic sum of charges carried out by central metal ion and ligands attached to it. For example, the charge number of FeCN6 4 minus, this complex sphere, this complex ion coordination sphere having the net charge is the 4 minus. Therefore, the charge number of this complex ion is the -4. Or it is also algebraic sum of charges of central metal ion and ligands. In this complex, the Fe is the central metal ion and cyanides are the ligands. The algebraic sum of these charges of this is called as the charge number. See here, the Fe having the +2 and this Cn cyanide having the -1 charge, and there are the 6 ligands, therefore it is the +2 -6 and is equal to the -4, and therefore the charge number of this complex pair is the -4. Also, this charge number is used to calculate the oxidation state or oxidation number of metal ion. For example, Fe in FeCN6 4 minus. We can calculate the oxidation number of Fe. The X is the oxidation number of Fe plus 6 into -1. The charge of cyanide is the -1. The total charge, the sum of these charges is equal to its net charge or charge number. Its charge number is the -4. Therefore, the oxidation number of this Fe, X minus 6 is equal to -4, and that's why X is equal to +2. The oxidation number of Fe is the +2. In this way, from this charge number, we can calculate the oxidation number of central metal ion. Now see, the next term which is used in the coordination compound is the coordination number, or it is also called as the Legancy. The coordination number of metal ion is in a complex is the number of ligand or donor atoms directly attached to it, or the number of electron pairs involved in the coordinate bond is called as the coordination number. The light transition metals having the coordination number 4 and 6, and heavier transition metal having the coordination number 8. In metal chelate, we know that the coordination number is equal to the number of ligands or donor atoms, or the electron pairs involved in the coordinate bond. We know that the chelating metals, that means which containing the polydentate ligands. In these chelating metals, the coordination number is not equal to the number of ligands, but it equal to the number of electron pairs donated by ligands. In chelating metals, the coordination number is equal to the number of electron pairs donated by ligands. For example, the CuEn2. In this example, this is the central metal ion and these are the ligands. There are the two ligands, only two ligands. If the Cn of the metal ion is equal to the number of ligands, but in this example there are the two ligands, but its coordination number is the 4. Because it is the bidentate ligands, there is the point of attachment is the 2. Therefore, this coordination number is not equal to the number of ligands, but it equal to the number of electron pairs donated by ligands. Therefore, 4 electron pairs which is donated by this ethylene diamine. And that's why the coordination number of this compound is the 4. Now see the next point, effective atomic number is called as the EAN number. First, know that what is the effective atomic number. The effective atomic number equal to total number of electrons around the central metal ion present in a complex. There are also EAN rule, which states that a metal ion continue to accept electron pairs till it attains the electronic configuration of the next noble gases, which is the EN number is equal to the 18, 36, 54, 86. Then the EN rule is obeyed by this complex coordination compound. If this compound having the EN number is equal to this noble gas electronic configuration, then it obeys the EAN rule. Then how to calculate the EAN number? The EAN number is equal to the number of electron of metal ion plus total number of electron donated by ligands. That is, it equal to the atomic number of metal Z minus number of electron lost by metal to form the ion X plus number of electrons donated by ligands Y. Then the formula of this EAN is the EAN is equal to Z minus X plus Y. Z is the oxidation atomic number of the metal, X is the oxidation number of metal ion, and Y is the number of electrons donated by ligands. Now see some examples of this calculation of EAN number. Consider the CONH3 6 3+. In this example, the oxidation state of this cobalt is the +3. The central metal ion is the cobalt, and these NH3 are the ligands. There are the 6 ligands which donate the 12 electrons. Then Z is equal to 27, X is equal to 3, Y is equal to 12. Then EAN is equal to Z minus X plus Y. And therefore, EN of this complex is the 27 minus 3 plus 12 is equal to 36. The EN number is the 36. That's why this complex obeys the EN number. In this way, in the next example, the Zn NH3 4 2 plus, Z is equal to 30, X is equal to 2, Y is equal to 8 because 4 ligands, 4 into 2, 8 electrons. Then EN is equal to Z minus X plus Y is equal to 30 minus 2 plus 8. EN is equal to 36. This example, this complex also obeys the EN rule because the EN number is the 36, which is equal to the noble gas electronic configuration. That's why it obeys the EAN rule. Now next example, FeCN 6 4 minus, Z is equal to 26, X is equal to 2, Y is equal to 12. Then EN, the formula of EN is equal to Z minus X plus Y is equal to 26 minus 2 plus 12. Therefore, EN is equal to 36. This compound also obeys the EN rule because the number is the 36, which is equal to the noble gas electronic configuration. If it is not equal to the noble gas electronic configuration, then it fails to the EAN rule. Now see the double salts and coordination complex. We see the difference between these double salts and coordination complex. That means double salts, they are the molecular solids. Also, they are addition compounds. They dissociate into simple ions in water and they lose their identity. For example, more salt. This more salt dissociate into the simple ions, positive and negative ions. And in coordination compounds, they are molecular solids or addition compounds. They dissociate into complex ions in water, but they retain their identity. For example, this K4FeCN6, when it dissociate in water, it dissociate as the K plus and FeCN6 4 minus. This is the complex ions. It dissociate into the counter ion and complex ions. But double salts, which are dissociate as the simple ions. The difference between this double salt and coordination compound is the double salt, when dissociate in water, it dissociate as the simple ions, but coordination compound dissociate in water, it dissociate as counter ion and complex ions. This is the difference between this double salt and coordination complex. In this way, we studied the all points in this first lecture. Thank you.